we're going to continue looking at the quality of tests and how to analyze the quality of tests. We've looked at type 1 and type 2 errors, both in discrete distributions and continuous distributions. Now we want to look at how we calculate the size and the power of a test. Two more characteristics that can be used to analyze the quality of a hypothesis test. So, the size and the power, let's go back to this matrix, to this array, to this two-way table, and we'll see where the size and the power come from. We already know that we have two conclusions that are correct conclusions for the test. Those are the top left and the bottom right, the two that are in blue. We have two errors that can be made. A type 1 error where you reject H0 and you shouldn't have, and a type 2 error where you accept H0 and you shouldn't have. The size of a hypothesis test is the same as the type 1 error. It's the probability of rejecting H0 when you shouldn't have. It's the probability of a type 1 error. So these two are synonymous. It's exactly the same process. Now, the power of a hypothesis test is actually the probability of correctly rejecting the null hypothesis. So here we realize we were using the wrong parameter, but how likely were we to have still got a correct conclusion even though that parameter was wrong? If the parameters are close, then the power of your test is going to be large. If the parameters are far away from each other, then the power of your test is going to be smaller. We can calculate this in two ways. It's true that the power is 1 minus the probability of a type 2 error. I would only ever use that technique if I'd already calculated a type 2 error, and then I can easily find its complement. I can easily just do 1 minus. But if you don't already have a type 2 error, there's another technique. Firstly, let's clarify that both of these terms, they relate to when we conclude the alternate hypothesis. They relate to when we've rejected H0. Because it's when we've rejected H0, that means we're calculating the critical region. So, for the size, it's the critical region with the old parameter. For the power, and that's why this table is useful to have in your head and to be able to reproduce. For the power, it's the probability of the critical region with the new parameter. Critical region with the old parameter, critical region with the new parameter. Both of these terms relate to concluding the alternate hypothesis, and both of these terms are calculated using the critical region. One with the old parameter, one with the new parameter. Let's have a look at an example. So, let's calculate the size and power of a test. Here we're told that a random variable x has a binomial distribution. A random sample of size 25 was taken to test the hypotheses p equals 0.3 against the alternate hypothesis p is less than 0.3. We're using a 10% level of significance. First we're asked to find the critical region for the test. So let's start with the distribution. So we have x follows a binomial of 25 and 0.3. From there we can get the expectation. Expectation is n times p. 25 times 0.3, that gets us 7.5. Okay, so the hypotheses were given in the question, but we'll always lay those out as well. Null hypothesis, p equals 0.3. Alternate hypothesis, less than 0.3. And the significance level, 10%. Okay, let's get this onto a diagram. So we know the minimum and the maximum for a binomial, so we can label 0 and 25. The expectation is 7.5. And we're looking for a region in the lower tail of 10%. So we want to try and figure out the critical value. A value that has less than 10% below it, we'll take that as our critical value. And if we can identify that critical value, then we have our critical region. Okay, let's try some probabilities. The probability that x is less than or equal to 5. So we can do a BCD on our calculator. Minimum of 0, maximum of 5, n is 25, p is 0.3. That gets us 0.1935. That's too big. So we'll try the next smaller number, so the consecutively smaller number. So probability x is less than or equal to 4. Now that gets us a probability of 0.0905. Here we are less than 10%. 4 is our critical value, which means our critical region is x is less than or equal to 4. That's what the question asks us to do in the first instance. We're then asked in part B to find the size of this test. Well, we know the size is the probability of a type 1 error. And we know that a type 1 error is going to be the probability of the critical region using the original parameter. So the critical region is the probability x is less than or equal to 4, and we're going to be using p as 0.3. Okay, so this is a BCD on the calculator. 0 is your minimum, 4 is your maximum, n is 25, p is 0.3. Okay, well that gets us 0.0905. That's the size. We could have got that straight away because we'd already calculated the probability to think about the critical region. But I want to show you how you'd go about it from scratch. Some questions may not ask you to have done the probability work for the critical region. Okay, let's move on to the power. Well, the power we saw from the matrix, from the two-way table, is the critical region, or the probability of the critical region, but using the new parameter. So this time round, we're still finding the probability x is less than or equal to 4, but we're using the new parameter, p equals 0.2. So a BCD, 0, 4, 25, 0.2, and this time round we get 0.4207. So the probability that even though we were using 0.3 when we should have been using 0.2, the probability we would still get the correct conclusion is 0.4207. Okay, so this is the size and power. This applies to discrete distributions and continuous distributions. Take some time now to work on some practice questions, and we'll come back to look at the power function next lesson. How could we get an expression for the power if we didn't know what the new parameter was? So we know our original parameter is incorrect, but we don't quite know what the new parameter is. How can we express the power?